So, hi and welcome everybody to the last lecture on digital communication course, which is titled Non-coherent Orthogonal Modulation. Basically, in this lecture, we will talk firstly about non-coherent binary frequency shift keying, and then we will also discuss non-coherent differential phase shift keying. So we all know that non-coherent version of modulation is so desirable because it provides us with low complexity transceiver architecture, and low complexity is very useful, very helpful for non-complex devices like Internet of Things devices. Non-coherent, when you hear the word non-coherent, this means that the phase information is not available at the receiver side. What does this mean? You don't need to generate a carrier at the receiver that has exactly the same phase as the transmitted carrier. And to do that, if you are assigned the task of making sure that the phase at the transmitter is the same as the phase at the receiver, you need to use and build complicated circuits. For example, phase locked loop circuit that can extract the phase and adjust it and make sure that both of them are matching. So due to this, when you have zero phase at the receiver, this can mean nothing about the phase at the transmitter. You don't know. Any modulation techniques that transmits information through the phase, such as binary phase shift keying, M-array phase shift keying, must be demodulated only coherently. Why? Because you are encoding your data bits into the phase of the carrier. Yes, the phase of the carrier. The phase is continuously changing, and it's very difficult to synchronize the phase. That's why if you are using phase shift keying, you can demodulate it only non-coherently. Only coherently, sorry. Phase coherent only, while amplitude and the frequency can be coherent, can be non-coherent, but it's possible to demodulate them non-coherently. So if you get a question in the final exam, which of the following cannot be modulated non-coherently? And both binary phase shift keying, frequency shift keying, amplitude shift keying. Non-coherently, phase shift keying. I cannot demodulate non-coherent. Yes, got it? Now, how to draw the constellation diagram? If you don't know the phase, do you know from where to place the first basis function? Like this, the first basis function here? You don't know where to place it actually. Yes? Because it's really difficult. You don't know the phase, you don't know the reference phase. So how are you gonna build the constellation diagram and put the symbol on it? It's difficult, not possible. So what do you do then? You don't have constellation diagram, but you can measure how far your received symbol energy from the origin. So you can measure the amplitude with respect to the origin, the power with respect to the origin, or the energy. It's impossible to draw the signal constellation since we don't know where the axes are. We don't know the phase. However, we can still determine the distance of each signal constellation from the origin. The origin is always fixed there. As a result of that, the modulation techniques that put information in the amplitude can be detected. So any modulation technique that puts the information in the amplitude of your carrier, you can detect it non-coherently. Frequency shift keying uses the amplitude of signals in two different frequencies, yes? You have two different frequencies we use in frequency shift keying, and since it affects the amplitude in a way or another, then this can be detected non-coherently, the frequency shift keying. Now, consider we have binary frequency shift keying. Binary means we have only two phases, two different values of the signal, which are represented by two different frequencies, F1 and F2. F1 corresponds for bit 1 and F2 for bit 0. The transmitted signal is given by psi of t square root of 2e over t cosine 2 pi I t plus theta. This is the frequency, this is the phase, and this is the amplitude of your carrier. For I1 and 2, and the duration from 0 to TB. If the carrier phase theta is unknown to the receiver, we can still be able to demodulate the transmitted signal using non-coherent demodulation. This is the beauty of non-coherent demodulation. You don't need to know the phase theta. Theta can be any theta, random. The previous binary phase shift keying signal can be rearranged as follows. Yes, this cosine A plus B is equal to cosine A cosine B minus sine A sine B. So we put it in this form. We just, instead of A and B, we put the actual values, theta and 2 by Fi. And then you end up having the basis function, which is the carrier phi 1 of t, phi 2 of t. What's phi 1 of t here? Cosine 2 by Fi t multiplied by square root of 2 over t. And what's Si1? Si1 is square root of e multiplied by cosine theta. Si of 2, Si of 2 here equal to square root of e sine theta, and theta 2 of t is the carrier actually, which is the basis function. Then now when someone tells you find the amplitude of this transmitted waveform, the amplitude is basically square root of the in phase square plus the quadrature square, the real part square plus the imaginary part square. You think of it like this because it has two terms, and these two terms are orthogonal to each other due to the basis function phi 1 and phi 2. So what's the result? The result is square root of e Si1. What's the value of Si1? I just told you square root of e cosine theta is square root of e cosine theta square plus e sine theta square, and cosine square plus sine square is equal to 1, and e can be taken as a common factor. Square root of e multiplied by 1 remains square root of e. Now Si1, how did we find Si1? We got the signal, the received signal, and we took its product with the phi 1 dot product operation, which means the projection of the signal along phi 1, and Si2 the projection of the signal along phi 2, which is the second basis function, and you get the projection alongside each axis, and then you can find the general amplitude value of your received signal. So this can be for any value, for any amplitude. Square root of integration from 0 to t xt, x of t can be any signal, not necessarily the signal that we discussed, s of t, multiplied by cosine 2 by Fi t plus the same factor but multiplied by sine instead of cosine, because this is the second basis function. And now you have this waveform, yes? You have this signal, this is this value, you can obtain it at the receiver. Now, how do you detect this non-coherently? Non-coherently means you are not knowing the phase of the carrier. You have to come up with ways to detect this non-coherently. If I tell you, mention 3 different ways of detecting the frequency shift keying signal non-coherently, you tell me the first way is to use quadrature receiver that uses correlators, or quadrature receiver that uses matched filter, or matched filter using envelope detector. Any one of these detection schemes can enable you to detect your data non-coherently. How do you implement the quadrature receiver using correlators? You take your data, the one you received, yes? You multiply it by cosine. See, I don't know the phase. The most important thing is cosine of a frequency. And you take the same data and multiply it by sine, then pass it through integrator, then this becomes dot product, and this also becomes dot product. And then, based on the equation here, there is a square here. Square. You need to do this square squarer, so you get the you get y in phase square, and here you get y quadrature square. You do the same, and then you sum. This is the sum between them. This is the sum. The sum here in the formula. See, I translated this formula into block diagram. After the sum, what remained? Square root. This. You pass it to another block that takes the square root, and then you get your output signal Li. Now, you use Li to decide whether it's 1 or 0 based on the value. Now this is a quadrature receiver with correlator. Correlator, where is the correlator? If I tell you, show me the correlator in this block diagram, this is the correlator. This multiplication with the integration, this is the correlation. Yes? Now with matched filter, instead of using correlator, this is the same, everything here the same, just instead of these two processes, you just matched filter. You use matched filter, and this filter is matched to the value of the basis function, cosine 2 pi fit, over the duration from 0 to t. And the same for the other branch. And you do, the other steps are exactly similar to the previous steps in the case of correlator. Clear? Using correlator, you use this. Using matched filter, you use this. Now, non-coherent matched filter using envelope detector. We said we have 3 ways. This way, using correlators, using matched filter, and using envelope detector. How to do that? Envelope means the amplitude of the signal. You have this equation, we agree on it. This equation represents the envelope. Yes, because it looks like the amplitude. Square root of the first part. When I give you a signal, a complex value, let's say, when I give you a complex value in Cartesian coordinate, like complex, give me example on a complex number. 5 plus J6, J5, J7, yes? If I tell you find this number, complex number, in polar coordinates, what do? You take the absolute value of this number, square root of 5 square plus 7 square. This is the absolute value. This is the same, but for the signal, not for one number, complex number, for a signal that has I and Q. And I, Q like real and imaginary. Clear? So this represents the envelope of the received signal. We can demodulate the received signal using an envelope detector. If this is the envelope, then we can use envelope detector. Detect just only the envelope. The envelope detector finds the square root of SI1 square plus SI2 square. In this case, what do? You pass your signals through matched filter, and instead of squarer and another squarer and sum and then comparison, you just put diode here where you detect the amplitude only, and then sample at t equal T capital. Non-coherent match filter envelope detector, an alternative way to show the equivalence between the non-coherent match filter using envelope detector and the non-coherent detector using quadrature detector is illustrated mathematically in the following slide. Now, we said that envelope detector is a way that we can use to detect non-coherent signals. Then this must be equal to quadrature receiver with matched filter, quadrature receiver with correlator. How do you prove that? Consider the output of y of t, a filter matched to cosine 2 pi fit. Then in this case, the output y of t is equal to x of t convolved with cosine 2 pi fit minus t small. And this is equal to the integration of x tau cosine 2 pi fi t capital minus t small plus tau. Tau is the delay, t is the instant time, and t capital, this is the shift, amount of shift you have. This is actually constant value that corresponds to the duration of 1 bit. Okay, and t, this is instantaneous value, changes with each second, I mean continuously. and tau, this is kind of a delay, and you integrate with respect to tau. This is actually coming from the convolution. When you convolve, you bring a new variable tau. So at the end of the day, when you do the convolution, you get this result, and you find out that the envelope of this value, this is the result of the convolution, is equal to this, which is exactly the same as correlator receiver. Yes, this value, this square, here there is no square root, it's to power 1 over 2. 1 over 2 is equal to square root, yes? Yes, and from math, 1 over 2 is equal to square root. That's why this is exactly similar to this equation. So both are equivalent. The one that comes from the envelope detector and the one that comes from the correlator or matched filter. Now, the block diagram of the generalized binary receiver for non-coherent orthogonal modulation. You have your signal, the signal you receive from your channel, and you pass it through matched filter to S1 of t, matched filter to S2 of t. Then you have envelope detector here, sample at t equal t capital, sample at t equal t capital, both in phase and the quadrature, and then you have comparison device. If this value, if the upper value, this value is greater than the lower value, then you choose that what was transmitted is S1. If it is below, then the symbol that was transmitted is S2. This is the decision rule that you use. If Li greater than Lk, then the estimated message is Mi. Yes? This is what you need to do actually. And then, what does this mean? That you have simple receiver structure that uses comparator. The only two things you need to do is pass your received data through matched filter and then take the envelope of it. Yes? And after the envelope, what do? You do the same thing with the quadrature component and then compare between them. The one that's larger, you decide on it, that this was transmitted. Quadrature receiver equivalent to either one of the two matched filter in part. So this is, the previous one was using matched filter envelope detector. This uses correlator square law device. So as you can see, the result of both of them is equivalent to each other. If you get your signal, multiply it by phi1 of t, which is the basis function, integrate it and then square it for the in phase and do the same for the quadrature, then you get the same. And here take the square root. Now, what's the average error probability of this scheme? Non-coherent frequency shift keying. The average error probability is half exponential to minus e over 2 n naught, where e is the simple energy and n naught over 2 is the power spectral density of the noise. So which one is better, this or binary phase shift keying? Of course, binary phase shift keying, because binary phase shift keying is coherent, and the error probability was half ERFC EB over N naught, which is lower than this value. This value is larger. For binary frequency shift keying, the transmitted symbols are defined as follows. The receiver can be implemented in these diagrams. The receiver, just like the previous block diagram was general for any frequency shift keying scheme, this is for binary when you have two values. The same, filter matched, envelope detector, comparison device. We are not bringing any new information here. The only thing that we modified it in such a way that it fits only the binary value of frequency shift keying, And the probability of error in this case is exactly equal to half exponential of to minus EB over 2 in naught, which is far less than the coherent modulation schemes like a QBSK, binary BBSK. So this is basically what's frequency shift keying non-coherent detection. It's not difficult, it's straightforward, and it actually simplifies your receiver structure design. So with this, we finish our discussion about frequency shift keying with non-coherent transceiver structure. And next, we move to discuss the other topic related to non-coherent binary phase shift keying.